It's really quite something when you stop and think about it, isn't it?
Yeah.
How many sophisticated control systems we interact with every single day.
Yeah, often without even realizing they're there doing their job.
Exactly. Like your car's cruise control, just smoothly adjusting speed, or, the climate system in your office, keeping things comfortable. These are all engineered brains hard at work.
Mm-hmm.
But what if we told you that the very foundation, the way we design these systems, is undergoing this, well, profound and pretty fascinating revolution?
That's right. Today, we're taking a deep dive into data-driven control systems. And this isn't just some technical jargon.
No.
It really represents a fundamental shift in how engineers are tackling some of the most complex control challenges out there, across the globe, really.
So traditionally, if you wanted to control a system, let's say, I don't know, a complex factory robot or maybe part of the power grid, the first step was always building this really intricate mathematical model of it.
Yeah, like creating a super precise, detailed blueprint of a house before you even think about starting construction.
Right. You'd need to map out every pipe, every wire, every single structural beam, get it all down on paper first.
But here's the big challenge, the fundamental issue. What if that blueprint is incredibly difficult, maybe even impossible to actually get?
Or what if the house itself is constantly changing, its shape, its internal structure?
Exactly. And that's precisely where data-driven control offers this really powerful alternative. Instead of needing that perfect explicit model, it directly uses the raw, real-world operational data right from the system itself to design its controller.
So it learns just by watching.
It essentially learns to control the system simply by observing how it behaves.
Yeah. Okay. So our mission in this deep dive is to really unpack this huge shift.
Hmm.
We want to explore why it's so incredibly important and maybe introduce you to some of the ingenious ways engineers are making systems smarter, more efficient, far more reliable,
Just by listening to the data.
just by deeply listening to the data they produce. Yeah. So get ready for some hopefully insightful aha moments.
Switch interesting.
So let's kick things off by trying to understand this great shift, moving from what we call model-based to data-driven control. For a very, very long time, model-based control was king.
Well, absolutely. It reigns supreme. If we go back to the early to mid 20th century, you had pioneers like Bode, Nyquist, Evans, Nichols,
The classics.
the classics, yeah. They developed what we now call classical control techniques. And these methods absolutely required knowing a system's transfer function.
Which is like its fingerprint.
Kind of, yeah. You can think of it as the system's unique fingerprint. It tells us precisely how it transforms an input signal into an output. And this function was typically derived from, physics equations or maybe simple, well-defined tests.
Assuming things were pretty straightforward, linear, predictable.
Exactly. Often assuming the system behaved linearly and predictably over time.
And then the 1960s brought another big leap forward, didn't they? The Kalman Revolution.
Yes, Rudolf Kalman, he introduced the state space concept and this notion of optimality, and that was a huge advance for model-based design. Well, it moved things beyond just looking at the external input-output view, like pressing the gas pedal and seeing the speed. It went to a deeper internal description of the system.
Ah, the state
Yeah.
itself.
It's like looking at a car not just by its speed, the output from the gas pedal, the input, but understanding its internal state, all those hidden variables that define its condition at any given moment, like its position and its velocity.
That sounds powerful. A deeper understanding.
It was incredibly powerful.
Yeah, you'd think that would solve everything, right? Make control design perfectly precise. But there were still underlying issues, weren't there? Even with these advanced methods.
That's exactly where we run into the, frankly, unavoidable problem of modeling errors. Because even with the most sophisticated methods, some level of modeling error is simply, well, unescapable, as the literature puts it.
Unescapable.
Imagine trying to perfectly map every tiny little nuance of a sprawling dynamic factory with hundreds of interacting parts, or maybe a complex biological system.
Yeah, forget it.
It's practically impossible to explicitly quantify all the uncertainties involved. Just too much going on.
So help me visualize this. How does that, arbitrarily small error become a potential real-world disaster?
It's a critical point, and maybe one that's often overlooked by designers. Even arbitrarily small modeling errors can lead to arbitrarily bad closed-loop performance.
Yeah.
So tiny inaccuracies in your mathematical model, maybe just a fraction of a percent off, can cause huge real-world problems.
Like what? Give me an example.
Okay, Think about a sophisticated aircraft. If its control system model has even tiny errors about its aerodynamics, or maybe its engine thrust under certain conditions,
Huh.
those tiny inaccuracies could potentially lead to wildly unstable flight or, worse, a crash.
So those early optimistic assumptions, the idea that you could get an almost perfect model.
They just didn't hold up, not in practical, high-stakes applications. The real world is messy.
Okay, so people tried to handle these uncertainties within that model-based world,
Wait.
right, with things like adaptive and robust control.
They did, yeah, and those methods were certainly helpful.
But they had limitations.
They did. They still demanded many prior plant assumptions about how the system behaves, and often required these costly Monte Carlo simulations.
Running tons of what-if scenarios.
Exactly. Running countless tests for different scenarios just to ensure robustness. And as industrial plants got more complex, think massive chemical facilities or these intricate energy grids,
Right.
the computational cost of doing all those tests just skyrocketed. It really highlighted the inherent limitations of relying on getting that perfect model, which was becoming increasingly unattainable.
And this is what really paved the way for data-driven control, I guess.
Exactly. That's the catalyst. Emerging strongly, maybe, end of the 1990s, this whole approach arose specifically to circumvent the necessity of deriving offline or online plant models.
To get around needing the model first.
Right. The realization was, hey, maybe we don't need to understand how the system works in every single tiny detail as long as we know what it does based on its data.
So it's like the operational data itself becomes the new blueprint.
Precisely. That's a great way to put it. Many modern plants today, they regularly generate and store huge amounts of operating data. Terabytes sometimes.
Okay.
And this data itself, maybe surprisingly, contains all the relevant information you need. Not just for control, but also for estimation, even for diagnosing faults.
So you don't have to build the perfect theory first.
You don't necessarily need to. The system's own observed behavior, captured right there in its data, tells you what you need to know to control it effectively.
Now, I've heard the terms data-driven and database thrown around.
Mm-hmm.
Is there a difference we should care about?
There is, yeah. It's a subtle but important distinction. While people often use them interchangeably, data-driven specifically means that both your starting point, the raw input-output measurements, and your destination, the controller you design, are derived solely from data.
Pure data.
Pure data, start to finish. Data-based is a bit broader. It might mean controllers designed without direct parametric models, but maybe there are some intermediate modeling steps involved somewhere. Our focus today is really on the truly data-driven stuff.
Got it. So what does this all mean for you, the listener? Why should you care about this shift? When does it really matter?
Well, the real takeaway here is this. If you're dealing with a system where getting an accurate mathematical model is just unavailable, too hard, too expensive,
Or just unreliable.
or unreliable, or where your initial assumptions about how the plant works just don't hold up reliably in the real world, then data-driven control offers a really practical, powerful solution.
It's how you avoid things going wrong.
It's how you avoid unstable or poorly performing systems, even when you're facing significant unknowns.
Okay. And to help us figure out when to apply these different approaches, it's useful to categorize systems, isn't it?
Yeah, thinking about the type of system helps. We can group them broadly. You've got simple systems, pretty straightforward, single inputs, single outputs, linear dynamics, easy stuff relatively.
Yeah.
Then complicated systems. These have multiple inputs, multiple outputs, maybe strong interactions between parts, but, and this is important, no emergence.
Emergence. What's that?
Emergence is where a property appears in the overall system that none of its individual parts possess on their own, like consciousness emerging from neurons maybe. Complicated systems don't have that.
Okay. No surprises like that.
Right. Then you have complex systems, strong interactions, and they can lead to emergence. New, unexpected properties can arise from the interactions.
Very trickier.
Definitely. And finally, complex adaptive systems. These not only have strong interactions and emergence, but their individual subsystems, or agents, can also adapt their behavior over time.
Like a city's traffic network.
That's a perfect example. Drivers adapt, routes change, things evolve.
That categorization really helps. And it leads to this useful box analogy, doesn't it?
Yeah.
For choosing your strategy.
It does. Think about it like this. Model-based control is great for white box problems.
White box, meaning you see everything inside.
Exactly. You have full quantitative information about the system's inner workings, like knowing every component value in a simple circuit diagram.
Okay.
Data-driven control, on the other hand, is ideal for gray box problems, where you have limited info, and especially for black box problems.
Where you basically just see inputs and outputs, nothing else.
Right. You've got input-output data, maybe, but no idea what's really going on inside. And what's fascinating, and maybe a bit surprising, is that most industrial processes today are actually gray box problems.
Really? Most of them?
Yeah, which makes these data-driven methods increasingly relevant and, frankly, incredibly powerful in the real world.
Okay, that makes a lot of sense. So with that foundation laid, let's dive into some specific methods, these ingenious solutions that bring the data-driven philosophy to life. Where should we start?
Okay, let's start with one called Unfalsified Adaptive Switching Supervisory Control. Bit of a mouthful, so let's call it UASC.
UASC. Got it. And what's the critical problem UASC is designed to tackle?
Okay, so UASC was introduced specifically to handle a really persistent challenge in traditional adaptive control.
Which was?
Systems that undergo rapid structural changes or sudden parameter shifts. Imagine, say, a drone whose weight suddenly shifts because it picks something up, or maybe its aerodynamics change dramatically in wind shear.
Traditional adaptive control struggles with that.
Often, yeah, it can struggle to keep up. UASC is designed precisely for these truly unknown and fast-changing systems.
Okay, so how does it actually work? Paint us a picture.
All right, imagine you have a control bank. It's like a library filled with a selection of pre-designed controllers. Maybe controller A works well at low speeds, controller B at high speeds, C handles disturbances well.
A toolkit of controllers.
Exactly. And then you have a supervisor unit. This unit is constantly monitoring the system's real-time input-output data. And here's the crucial part. It doesn't just look at the controller that's currently active.
No. What else does it do?
It estimates the performance of all the candidate controllers in its bank, even the ones sitting on the shelf not currently being used. We'll get to that. But based on these performance estimates, it intelligently switches to the one that it predicts will perform best right now.
Okay, switching controllers on the fly. But you mentioned something really interesting earlier. It's philosophical underpinning, something about Karl Popper.
Yes. This is where it gets, I think, really insightful. UASC is based on Karl Popper's theory of falsification from the philosophy of science.
Okay. How does philosophy connect to control systems?
Well, Popper argued that a scientific theory isn't really proven true by confirming it again and again. Instead, what makes a theory scientific is that it's falsifiable, meaning you can imagine an experiment or observation, some data that could contradict its claims.
So you test it by trying to break it, essentially.
Exactly. In UASC, a controller is falsified if its actual performance, measured by some cost function, like how far off target it is, gets worse than a predefined threshold, or if it's clearly performing worse than another candidate controller in the bank.
So it's not about proving one is good, but proving others are bad.
Kind of. The core idea, the insight, is that instead of trying to prove a controller works perfectly, UASC focuses on quickly disproving or falsifying the ones that are performing badly or might destabilize the system.
Mimicking how science progresses, you said.
Right, learning robustly by efficiently weeding out what doesn't work. And this radically speeds up safe deployment because it allows the system to quickly disconnect and discard potentially destabilizing controllers without ever actually putting them in the main control loop first if they fail the test.
That's incredibly clever. Safety first. But okay, how does it evaluate those inactive controllers if they're not actually, controlling the system at that moment?
Ah, great question. It uses something called a virtual reference signal.
Virtual. So
Yeah.
not real.
Not a real signal being fed in, no. It's a hypothetical input. The system calculates, okay, given the output we just saw from the real system, what input would have been needed if, say, inactive controller C had been in charge to produce that same output?
Whoa. Okay, run that by me again.
It's like running what-if scenarios constantly in the background. Based on the actual system behavior, it figures out what each inactive controller would have done, or rather, what input would have made it behave that way. This lets it compare their potential performance without actually trying them out live if they look bad.
So it's testing them virtually. That's neat. What about stability? Does all this switching compromise the system's stability?
You'd think it might, but no. It's designed very carefully. It ensures stability through something called incremental stability.
Incremental stability.
Yeah, basically it means that no matter how two different solutions or trajectories of the system start out, if they're both controlled by the UASC scheme, their behaviors will eventually converge and become virtually identical.
So it's robust and predictable in the long run.
Exactly. Makes the system incredibly robust and predictable, even with the switching. For simply linear systems, this just boils down to standard stability guarantees we're familiar with.
And this isn't just theory locked away in papers, right? Where has UASC actually been used?
Oh, it's been applied to some really critical, challenging real-world systems. Things like dynamic positioning of marine vessels, keeping oil rigs or supply ships perfectly stationary in choppy seas and strong currents.
Wow.
Autopilot design for extremely maneuverable missiles, which have highly nonlinear flight dynamics that change incredibly fast.
Makes sense.
Even precise control of micro-aerial vehicles, drones, with all their inherent nonlinearities and rapid changes in dynamics.
So aerospace, marine, anywhere else.
Yeah, also in process control, like continuous non-minimum phase stirred tank reactors, tricky chemical reactors, and controlling nonlinear robot manipulators, where things like how much the robot arm bends or delays in the motors are incredibly hard to model perfectly.
So really complex, hard to model stuff. Are there ways to make it perform even better, refinements?
Yes, absolutely. Techniques like the threshold hysteresis algorithm, or THSA, have been developed. They help the supervisor select stabilizing controllers faster and also help mitigate something called the DAL phenomenon, destabilizing active loop. Basically, it's a situation where switching could temporarily cause dangerously large signals before the system settles down. THSA helps avoid that.
Okay, so UASC gives us this powerful way to adapt by smartly switching between pre-designed controllers based on data. But what if you could just directly calculate the controller you need, maybe in one shot, without needing that whole bank of options?
Now you're teeing up our next method perfectly.
That sounds like the goal of virtual reference feedback tuning, or VRFT.
That's precisely right. The goal of VRFT is, well, pretty straightforward conceptually. Instead of spending all that effort trying to identify the plant's intricate internal mathematical workings.
The blueprint again.
Right. VRFT aims to directly design a controller so that the overall closed-loop system, the plant plus the controller, behaves exactly like some desired reference model you specify.
So you say, I want this system to act like this ideal system.
Exactly. And it's often called a one-shot approach because, ideally, it directly computes the controller parameters you need from a batch of data.
And the beauty I think you mentioned is you generally don't need the plant's actual mathematical model, just its input-output data.
Exactly. You just need a recording of how the system responded to some inputs in the past. That's what makes it so versatile for systems where getting that precise internal model is just too difficult or maybe even impossible.
Okay, now explain the virtual reference input magic again. That was a key concept for UASC too, but how does it work here?
It's a similar idea but used differently. In VRFT, imagine you have your desired output from the system, what you want it to do according to your reference model. VRFT looks at the actual measured output from the real system, from your data, and asks, what hypothetical input, if I fed it into my ideal reference model, would have produced that actual measured output?
Okay, so it's working backward from the real output using the ideal model.
Precisely. It calculates this virtual reference input. And the clever trick, the aha moment here, is that this transforms the difficult controller design problem into a much simpler identification problem.
How so?
Because now you essentially have pairs of data. The virtual reference input, what should have gone into the ideal system, and the actual input that went into the real plant to produce the observed output. The controller's job is simply to transform that virtual reference into the actual input. So designing the controller becomes like identifying a system that maps one signal to the other.
That is clever. It bypasses needing the actual plant model for the controller design itself. But real-world data, it's always noisy, right? How does VRFT handle that? You don't want noise messing up your controller.
Great point. Noise is always a factor. VRFT typically tackles this using an instrumental variable approach. This is a statistical technique designed specifically to prevent biased estimations when your measurements are corrupted by noise.
Instrumental variables. Does that involve modeling the plant after all?
Here's the fascinating part. Yes, calculating these instrumental variables does involve identifying a model of the plant. However, this plant model is only used to generate the instrumental variables needed to clean up the estimation process. It's not used for designing the controller itself.
So you can use a really complex high-order model just for the noise canceling part?
Exactly. You can identify a very detailed internal model just to get good instrumental variables and handle the noise effectively without making your actual controller complicated or needing to trust that model for the final control design. The controller structure can remain simple.
That's a neat separation. And it even handles something called the non-minimum phase challenge. That sounds tricky. What is that?
It can be very tricky. Some systems, called non-minimum phase plants, have these peculiar characteristics. Mathematically, they have zeros outside a specific stability region in the complex plane.
Okay, translating that to English.
Practically, it often means the system initially responds in the opposite direction to what you intend. Imagine pushing something forward, and it first jerks backward slightly before moving forward.
Like a car reversing a tiny bit when you hit the gas? Weird.
Exactly, that kind of counterintuitive initial response. Those non-minimum phase zeros describe that, and they make control much harder, potentially leading to unstable controllers or internal instabilities if you're not careful.
So how does VRFT deal with these awkward systems?
VRT handles this quite elegantly. It requires that the desired reference model you choose also has these same non-minimum phase zeros.
So the ideal model has to have the same weird initial behavior.
Essentially, yes. It absorbs the difficult behavior into the target specification. This often involves making the locations of the reference model's zeros free parameters that you can optimize as part of the design process, letting the ideal model adapt to the plant's inherent quirks.
Okay, so for you listening, this VRFT approach is kind of like saying, look, I don't really care how this engine works internally, all its weird noises and vibrations. I just want it to accelerate smoothly like that ideal engine over there. And VRFT then figures out the necessary commands based purely on observing the real engine's past behavior to make it match that ideal performance without ever needing the full engine schematics.
That's a really good analogy. It focuses on matching the desired behavior using available data.
Makes intuitive sense. Now, VRFT gives us this powerful direct design method. But sometimes the problem isn't designing from scratch. Maybe it's about optimizing or tuning an existing controller, especially in a really complex system where you just can't calculate the best direction to adjust things.
Right. You know you want to minimize some cost, like energy use or error, but you don't know which way to turn the knobs.
Exactly. And that sounds like where something like simultaneous perturbation stochastic approximation, or SPSA, really shines. Tell us about its gradient-free power.
Okay, so many optimization problems in control rely on knowing the gradient.
Which is just the direction of steepest change, right? Like finding the quickest way down a hill.
Exactly. You calculate the slope and you head downhill. You need that gradient information of your cost function, the hill, to find the optimal solution, the bottom of the valley. But for really complex, maybe unknown systems, calculating that gradient directly might be impossible or just computationally way too expensive.
So SPSA gets around needing the gradient.
Yes, SPSA is a multivariate stochastic optimization technique that does not depend on such direct gradient information. It doesn't need the exact slope. Instead, it makes these really clever, efficient approximations of the gradient direction using only noisy measurements of the objective function itself.
How does it do that without the slope?
It does it by simultaneously wiggling all the parameters slightly in random directions, measures the cost function just twice, and uses that information to estimate the gradient direction. It's stochastic, meaning random, but statistically, it points downhill on average.
Okay, so it's often called a tuning algorithm.
Exactly, because its primary goal is to iteratively find the optimal parameters for a controller like tuning the PIND gains in a PID controller that minimize some performance cost function, like minimizing tracking error or control effort.
And you mentioned it's remarkably efficient, especially if you have lots of parameters to tune, maybe like in a neural controller.
Absolutely. That's one of its biggest strengths. SPSA typically only needs 2 measurements of the cost function per iteration, regardless of how many parameters you're tuning simultaneously, whether it's 3 parameters or 3,000.
Only 2. That's a huge advantage over methods where the cost scales with the number of parameters.
A massive computational saving, yeah. Makes it really practical for high-dimensional optimization problems where traditional gradient calculation would be prohibitive.
Okay, this sounds incredibly useful for messy real-world problems. Could you give us some concrete examples, maybe in those complex under-actuated systems you mentioned?
Sure, a classic example is the liquid slosh system.
Liquid slosh, like fuel in a rocket.
Exactly. Or oil sloshing around in a tanker truck or water in a ship's ballast tanks. This sloshing creates these destabilizing forces that can really degrade the system's performance or worse, even cause dangerous overturning.
So how does SPSA help?
SPSA has been successfully used to control such a system. For instance, simultaneously tracking a desired horizontal motion for the container while actively regulating the slosh angle of the liquid to zero, keeping it calm. And it does this purely by tuning the gains of, say, a PID controller, using only input-output data without needing an explicit, complex fluid dynamics model of the sloshing.
Wow, just learning from the wiggles. What about the ball and beam system? That's another classic control challenge, isn't it?
It is. It's a benchmark problem, often used to model things like, believe it or not, aspects of automobile suspension or aircraft stabilization. It's inherently unstable balancing a ball on a beam.
Right, hard to do by hand.
Very. STSA can help here too. It can learn the controller parameters needed to place the ball precisely at a desired point on the moving beam, while also keeping the beam itself horizontal, again, learning directly from observed data, navigating the system's inherent instability without needing a detailed physical model derived from first principles.
So, for you listening, if you're faced with tuning something incredibly complex, maybe optimizing a chemical process or training a robot or finding the best parameters for a financial model, but you don't have a neat formula or a precise instruction manual telling you which way to adjust things, SPSA is like having this super smart, incredibly efficient trial and error system. It doesn't need the underlying formula. It just intelligently probes the system and quickly zeroes in on the optimal settings.
That's a great way to think about it. It's a powerful search algorithm for optimization in the absence of explicit gradient information.
Okay, now we shift gears a bit to something you called a truly behavioral breakthrough. Data-driven control based on Willem's fundamental lemma. That sounds fundamental.
It really is a cornerstone of what's called behavioral systems theory. Jan Willem's fundamental lemma is quite profound. It states that for any linear time invariant system,
Okay, linear system, constant over time.
right, for any such system, a single sufficiently long input-output data trajectory, just one recording of inputs and corresponding outputs, provided the input was persistently exciting.
Persistently exciting, meaning the input was rich enough, jiggled the system enough.
Exactly. It needs to be rich enough to excite all the system's internal dynamic modes, like shining a bright light into every corner of a room to see everything hidden within. If you have that one good data set,
Then what?
then that single data trajectory contains all the information needed to describe or predict every other possible input-output trajectory of that same system.
Wait, all possible behaviors are captured in just one sufficiently long, exciting experiment.
Essentially, yes. For linear time invariant systems, it's a very powerful statement.
So it implies the data itself is the model, rather than just being information about some underlying mathematical model.
That's the core idea of the behavioral approach. You don't necessarily need a traditional mathematical model like state space equations or a transfer function to understand and predict the system's behavior. The data itself, properly organized, is the model.
And how is it organized? You mentioned a Henkel matrix.
Yes, the Hankel matrix is the mathematical tool used here. It's a specific way of arranging the past input and output data into a large matrix. This matrix structure inherently captures the system's dynamics. It builds the structured memory of the system's past actions that allows prediction.
Okay. And this concept, this fundamental lemma, has led to a practical control approach called data-driven predictive control, or DPC.
Exactly. DPC leverages this lemma directly for control. Now, model predictive control, MPC, is already widely used in industry, right? It predicts future behavior and optimizes control moves over a horizon.
Right, but MPC usually needs a really accurate system model.
Critically, yes, that's its main bottleneck. DPC, built directly on Willem's fundamental lemma, is revolutionary because it does not employ a parametric system representation.
Meaning no explicit, predefined mathematical model needed.
Precisely. The core insight is that instead of going through the often difficult step of identifying complex equations first, DPC learns the system's entire input-output behavior directly from that Hankel matrix of past data.
So it skips the modeling step.
It largely avoids the need for complex system identification and also state estimation, which are often tricky parts of traditional MPC. This makes it potentially much simpler to implement, especially for systems that are unknown or poorly modeled.
How does it work then? How does it make control decisions?
It formulates an optimization problem very similar to traditional MPC, minimizing future errors, penalizing control effort, respecting constraints. But instead of using a model to predict the future, it uses that Hankel matrix, that historical data, to directly predict future behavior and find the best sequence of control inputs.
It predicts the future purely based on past patterns in the data.
That's the essence of it.
Can you give us an example where DPC has been put to the test?
Sure. For instance, DPC has been successfully applied to track changing set point trajectories in multi-output systems, like a laboratory four-tank system. It effectively controlled the liquid levels and flows between the tanks, even though the interactions are complex, and it did this without needing a priori knowledge of the tank dimensions or flow coefficients. It could even find optimal steady-state control signals directly from the data.
That's impressive. What about nonlinear systems? The lemma was for linear systems, right?
Good catch. The original lemma is for LTI systems. However, the DPC idea has been cleverly extended. It can be used to control unknown nonlinear systems too, by performing what's called local linearization around artificial steady states that are derived purely from the input-output data. Basically, it assumes the system behaves linearly for small deviations around its current operating point, and it constantly updates this local linear approximation using the most recent data in the Hankel matrix.
So it's always adapting its local view of the nonlinear system.
Exactly. An example application is controlling a DC motor to track a desired angular velocity, even though a motor's behavior can have nonlinear friction or torque characteristics, especially under varying loads. DPC can handle that by continually updating its data-driven predictive model.
Okay, so for you listening, this concept is genuinely groundbreaking. Instead of trying to reverse engineer the complex rules or equations governing a system, Willem's lemma and DPC suggest you just need a really thorough recording of its past actions, inputs and outputs, under sufficient excitation. And that recording inherently contains enough information to perfectly predict its future actions, at least for linear systems, or locally for nonlinear ones.
It's a powerful shift in perspective.
It really is. It's almost like predicting the weather purely by observing incredibly detailed past weather patterns without needing a full, complex model of atmospheric physics. It's pure, data-driven prediction and control.
That's a good analogy for the core idea.
Now, sticking with the challenge of nonlinear systems, which are everywhere, let's dive into data-driven control based on Koopman theory. You mentioned Koopman offers an elegant way to handle nonlinearity. How does it work?
Right, so Koopman theory is another fascinating approach. Nonlinear systems are notoriously hard to analyze and control because the principle of superposition doesn't hold. You can't just add solutions together.
Things get complicated fast.
Very fast. Koopman theory offers this almost magical perspective. It proposes that any nonlinear dynamical system, no matter how complex, can actually be represented as an infinite dimensional linear system.
Infinite dimensional. Okay, that sounds abstract. But linear.
Linear, but not in the original state space. It's linear in a different, usually infinite dimensional space of observable functions of the original state. Think of transforming your perspective, looking at the system through a different set of goggles, and in that new view, the evolution looks linear.
So you transform the problem into a linear one, even if it's infinite dimensional. Why is that helpful?
Because it allows us to bring the entire powerful toolkit of linear systems theory and linear control designed to bear on these inherently nonlinear problems, which would otherwise be intractable.
And the Koopman operator is the key mathematical object here.
Exactly. The Koopman operator is the fundamental linear operator that describes how these chosen observable functions evolve linearly over time. If you can find this operator, you've essentially linearized the system's dynamics in this new function space.
And finding its eigenfunctions is important.
Yes. Eigenfunctions are special observable functions that, when acted upon by the Koopman operator, simply get scaled by a constant factor, the eigenvalue. Their fundamental shape in this function space doesn't change. Finding these eigenfunctions and eigenvalues is key because they reveal the underlying linear modes and frequencies governing the nonlinear system's behavior. They unlock that linear view.
Okay, but infinite dimensions. How on earth do we apply this in practice? We don't exactly have infinite dimensional computers lying around.
Excellent question. That's where the data-driven aspect comes in strongly, through a technique called dynamic mode decomposition, or DMD.
DMD, what does that do?
DMD is a data-driven numerical algorithm. It takes snapshot data from your system measurements over time, and it finds a finite dimensional approximation of the Koopman operator directly from that data.
So it brings it back from infinity to something manageable.
Precisely. It's like finding the hidden dominant linear modes or patterns within your complex, high-dimensional, potentially nonlinear data. It tries to find the best linear operator that approximates how the system evolves from one snapshot to the next.
How does it extract these modes efficiently?
It typically uses singular value decomposition, or SVD, which is a really powerful workhorse tool from linear algebra. SVD helps break down the complex data matrix into its fundamental, most energetic components or modes, much like, say, separating a complex musical chord into its individual notes to understand its structure. DMD leverages SVD to find those dominant dynamic modes related to the Koopman operator.
And the big advantage here, again, is that DMD does not require knowledge of the governing equations.
Exactly. It works purely from data snapshots, and it's naturally formulated in tractable linear algebra, meaning we can use standard efficient numerical methods to compute it.
Which leads us directly to data-driven Koopman predictive control, or DDKPC.
You got it. DDKPC combines Koopman theory, approximated via DMD from data, with the framework of model predictive control. So you get predictive control, but for nonlinear systems, using a linear model learned directly from data.
I think you can handle noise too.
Yes, extensions of DDKPC have been developed that explicitly incorporate robustness to measurement noise, which is crucial for real-world applications.
Speaking of which, there's a fantastic real-world case study, the Khaki-Sedigh solar collector field at a solar power plant in Spain. How is DDKPC used there?
Right, that's a great example. The Khaki-Sedigh field has rows of parabolic troughs that collect solar energy to heat oil. Controlling the outlet oil temperature is critical but challenging due to the nonlinear dynamics, time delays, and disturbances like passing clouds affecting solar radiation or changes in ambient temperature.
Sounds complex.
Very. DDKPC has been successfully used there to control that outlet temperature even with unknown system parameters like heat transfer coefficients. And in the presence of those measured disturbances, it learned a linear predictive model using the Koopman-DMD approach from operational data and used it for MPC.
That really shows its potential for practical, large-scale industrial processes, doesn't it? Especially ones that are inherently nonlinear.
Absolutely.
So for you listening, maybe think about it like this. Imagine trying to understand the complex swirling patterns in a fluid flow, or maybe the seemingly chaotic movements of a flock of birds. Koopman theory and DMD are like finding the hidden, underlying, simple linear rules or modes that govern the overall behavior, even if the individual particle or bird movements are highly nonlinear. And finding these linear rules, just from observing the system, allows us to predict and potentially influence the entire complex flow or flock.
That captures the essence well, finding the linear structure hidden within the nonlinear dynamics using data.
Very powerful concept. Okay, finally, let's arrive at model-free adaptive control, or MFAC. Now this one sounds like the ultimate black box champion, doesn't it?
It really does. If you're in a situation where you have absolutely no precise quantitative information about the plant, no physics model, no equations, and crucially, no system identification techniques are utilized in the controller design process itself, then MFAC is often your go-to approach.
So truly model-free. You just observe inputs and outputs, and the system learns to control itself.
Pretty much, yeah. It fully embodies that black box philosophy.
What are its key features? Does it still offer any guarantees, like stability? That seems like a big ask for something completely model-free.
It does seem like a big ask, but remarkably, yes. Its key features are quite compelling. It generally requires only minimum plant assumptions, very basic things about smoothness or boundedness. It aims to avoid complicated tuning procedures that often plague other adaptive or robust controllers. And perhaps most importantly, many MFA schemes come with rigorous mathematical proofs for closed-loop stability.
Stability proofs even without a model. That's significant.
It is. That's a major theoretical underpinning for MFAC.
Okay, so the brilliance of MSE, as I understand it, lies in this dynamic linearization method. How does that let it control pretty much any discrete time nonlinear system using only input-output data? That sounds like magic.
It's quite ingenious, maybe not magic, but very clever. MFAC doesn't try to find the true underlying nonlinear equations of the system because it assumes you don't know them. Instead, it focuses on learning an approximation of how the system responds to small changes locally and dynamically.
Locally and dynamically, meaning right here, right now.
Exactly. It essentially tries to figure out a kind of pseudo-gradient or sensitivity on the fly purely from recent input-output data, even though you don't know the real global mathematical function.
How does it represent this pseudo-gradient?
It uses these time-varying parameters, which are estimated online from data. For simpler systems, it might use the pseudo-partial derivative, or PPD. For more complex systems, maybe the pseudo-gradient, or PG. And for the most general multi-input multi-output case, the pseudo-Jacobian matrix, or PJM.
Pseudo-Jacobian matrix.
Right. These pseudo-terms are the core of the dynamic linearization. They are dynamic, meaning they are constantly updated from the latest input-output data, reflecting the ever-changing local sensitivity or behavior of the system without needing a complete fixed model. The existence of this PJM, which effectively compacts all the system's complex characteristics into this single data-driven, time-varying parameter matrix, is even theoretically proven under certain assumptions.
Okay, so it's constantly learning and updating its estimate of how the system behaves locally right now. And then how does it use that to decide on the control action?
Based on that estimated pseudo-derivative or pseudo-Jacobian, MFAC then derives control laws. These laws are typically designed to minimize a one-step-ahead cost function, trying to make the system output match the desired reference signal on the next time step, using the learned local sensitivity.
And what if the system itself changes over time? Its actual characteristics drift.
Good question. For systems whose characteristics might change more significantly over time-varying plants, MFC often incorporates a reset mechanism. If the estimated parameters, like the PJM, seem to be diverging or behaving strangely, the algorithm can periodically reset them, forcing it to relearn the local dynamics quickly, which helps maintain good performance.
Does this whole approach extend nicely to systems with multiple inputs and outputs? Those interactions can be tricky.
Yes, it does. MFAC has been extended to multivariable systems. It often relies on estimating that full pseudo-Jacobian matrix and sometimes uses data-based concepts related to diagonal dominance to help manage the interactions between different control loops effectively.
Okay, we've seen it applied in case studies, like the continuous stirred tank reactor, CSTR. Can you maybe elaborate on that and perhaps touch on a powerful hybrid approach you mentioned earlier?
Sure. In the CSTR example, which is a common benchmark in chemical process control, different variants of MFC using the simpler CFDL, compact form dynamic linearization with PPD, or the more complex FFDL, full form with PJM, have been shown to effectively control the reactor temperature and concentration, highlighting how the choice of linearization model can impact performance.
And the hybrid approach with SPSA.
Right. That was a really neat application. Remember the liquid slosh system we talked about with SPSA?
Inherently unstable.
Exactly. In some cases, a system might be open-loop unstable, meaning MSC might struggle to stabilize it initially just from I/O data. So in a powerful hybrid design, SPSA was used as an inner-loop controller. Its job was simply to stabilize the unstable slosh dynamics first, using its efficient tuning.
So SPSA gets it under control. Then what?
Once SPSA stabilized it, MFAC took over in an outer loop. Its job was then to ensure optimal performance, making the system track the desired trajectory accurately and efficiently, leveraging its adaptive capabilities now that the system was stable.
That's a brilliant synergy. Using SPSA for stabilization and MFA for performance optimization, both data-driven.
It really shows how these different data-driven tools can be combined effectively.
Okay, so for you listening, MFAC feels like the ultimate learn-by-doing approach for a machine. It's like, imagine trying to teach a child to ride a bicycle. You don't give them a complex physics model of their body, the bike, gravity, friction.
Yeah, no.
Instead, they learn through countless tiny adjustments based on their last wobble output and how they tried to steer or pedal input. They make a small pseudo-correction. They're constantly updating their internal model of how to stay balanced right here, right now.
That's a fantastic analogy for the dynamic linearization idea.
That's essentially what MFAC's dynamic linearization does for a machine controller. It's all about achieving complex control purely through direct observation and rapid adaptation without ever needing the original instruction manual.
Exactly. Learning the local input-output relationship directly from data and using it for control.
Wow. Okay, so we have really journeyed through this fascinating world of data-driven control today. We started with its origins, as this powerful alternative to the traditional model-based methods.
Tackling those unavoidable modeling errors.
Right. And then we dove into some specific, really ingenious schemes. UASC, the switching supervisor.
VRFT for direct one-shot design.
SPSA for gradient-free optimization.
DPC using Willems lemma and that Hankel matrix of data.
The Koopman-based DDKPC for tackling nonlinear systems by finding linear structure.
And finally MFA, the truly model-free adaptive approach.
And each one offers these unique and really powerful ways to harness the information sitting right there in the operational data. Often, remarkably, without needing those explicit mathematical models we thought were essential for so long.
And it's important to remember this shift isn't just about, tweaking algorithms slightly. It really feels like a fundamental change in how we approach the whole problem of controlling complex, uncertain, maybe even truly unknown systems.
Yeah. It prioritizes practical results, doesn't it?
Yeah.
And robust performance in the real world,
Yeah.
maybe overachieving a theoretically perfect model that might not hold up anyway.
Exactly. Which makes it ideally suited for all those gray box and black box problems that, as we discuss, are actually so prevalent in today's interconnected, complex, industrial, and technological world.
Okay, so as we wrap up this deep dive, here's maybe a provocative thought for you, our listeners, to mull over. Think about any intelligent system around you. Maybe it's a smart thermostat learning your habits. Maybe it's a sophisticated robotic arm in a factory. Or perhaps even the incredibly complex systems that guide a spacecraft navigating the unpredictable environment of deep space.
Hmm.
How much of its actual intelligence, its reliable operation, its ability to adapt, how much of that might be derived not from some perfect pre-programmed internal model of its world, but actually from its profound ability to continuously observe, learn, and adapt its control strategies directly, purely from the stream of data it collects.
That's a great question. Where does the real smarts come from? The prior model or the ongoing learning?
Right. And thinking further, what new, perhaps currently unimagined, possibilities open up for creating truly intelligent, adaptable, and resilient systems when we fully embrace the power of observed data over the perhaps elusive goal of precise, explicit knowledge of all the underlying mechanisms.
It definitely opens up new horizons for control design, pushing the boundaries of what we can automate and optimize.
Something to think about.